Again from the Chapman book, and the last example, it covers many aspects, determining the parameters, equivalent parameters, and also doing the voltage regulation, calculating the voltage regulation, and also drawing the plots, the phasor diagrams, and then finally we have to calculate the efficiency of the transformer. So this is what we have: a 15 kVA transformer. Again, it is step down transformer. High voltage side is the primary side and 230 volts is the secondary side. And we have to determine excitation branch components and its series impedances and the voltage regulation. And one of the most important thing again is the following data, test data have been taken from the primary side of the transformer. Okay, so whatever values we will calculate from these values, and we know that open circuit test is used to calculate RCP and XMP, the magnetization branch, and the short circuit test is used to calculate R equivalent P and X equivalent P. All these components will be reflected towards the primary side. What I mean by that is that we will see further, and we have already calculated the values in the previous example and also in the previous examples. So we know that theta is equals to cos inverse POC over VOC IOC, and we also know by this method we use the admittance method, and you can also use the other method, individually calculating everything. So by these values we are able to calculate RCP and XMP, and the value of RCP will be 105 kilo ohms and XM will be 11 kilo ohms. So this was open circuit test, and with the short circuit test, what we can calculate is again P short circuit, V short circuit, I short circuit, and we calculate the Z is V short circuit over I short circuit, and with the angle theta, and from here we are able to calculate R equivalent P, and the value for the R equivalent P will be 4.45 ohms, and for X equivalent P that will be equals to 6.45 ohms. So these are the values that we have calculated. Now transfer referred to the high voltage side. So what do we mean by high voltage side? In this case it is the primary side, and this is low voltage side is the secondary side. So let's draw these two circuits. First refer to the primary and then refer to the secondary. So let's see, and there is the circuit. This I am actually part 1. And where we have, these are the values. So this is RCP, this is XMP, this is R equivalent P, this is X equivalent P. And this is referred to the prime, this is high voltage side, primary side. So here is actually VH equals to VP, and the current is high voltage side current, that is equals to the primary current. And here we have AVL, or that is AV as secondary side, that is the low voltage side, and the current will be the secondary current divided by A. So this is the equivalent circuit, and we have calculated the values, so we can write the values. This will be 105 kilo ohms, this will be 11 kilo ohms, R equivalent will be 4.45 kilo ohms, this not kilo ohms, sorry, ohms, and this will be 6.45 ohms here that we calculated. So this is actually referred to the high voltage side, referred to the primary. The second part states that we have to calculate, refer to the low voltage side. LV side in our transformer is the secondary side. Now we know the method of reflecting. When we have to reflect towards the primary side, we multiply by a square the impedances, but when we refer to the secondary side, we divide by a square. So all the impedances in our circuit will be divided by a square. So what is a square, or what is a? A is turns ratio, primary over secondary, and we have 2300 divided by 230, that becomes 10. So all these impedances, if you draw again, so this is the circuit, and here it is actually referred to the secondary side. So the secondary voltage, that is the low side voltage, is here, and here the current is also, that is the secondary current. But on the primary side, the voltages will be VH divided by A, that is actually VP divided by A, and the current will be AIH, that is AIP. Okay, and this is RC secondary, and this is XM secondary, this is R equivalent secondary, and this is X equivalent secondary. So how we can calculate these values? And this will be, if we will divide the values of RCP, this is actually equals to, what was the value of the primary divided by a square? 105K divided by 10 square, and this will become 1050 ohms. Similarly, all the values, if you divide this value with a square, the value will become 110 ohms. If you divide this value with a square, it will become 0.045 ohms, and this value divided by a square, it will become 0.0045 ohms. So this is the transformer circuit answer of the part B. Equivalent circuit refer to the low voltage side. Low voltage side, and in this case it was the secondary side. So in the part C of this example, what we see is that calculate the full load voltage regulation. Full load voltage regulation. In the previous example, sometimes it would say 75% of the full load, but here it is referring to full load regulation at 0.8 lagging power factor, unity power factor, and 0.8 leading power factor. So let's first determine, and as we have seen previously, we can either use this circuit to calculate voltage regulation or this circuit to calculate voltage regulation. Let's use this circuit to calculate the voltage regulation. So first of all, we have to determine what is the full load status for our circuit, and S is equals to 15 kVA, that is 15,000 VA. So we can calculate the full load current. I full load will be equals to the rated power divided by the voltage. Now we are calculating this. So we have calculated the full load current, and we have the rated voltage at the secondary side, and the rated voltage at secondary side is 230 volts. So the current I full load current, that is on the secondary side of the transformer, we have calculated it to be 65.2 amperes. Okay, now the important thing is we have calculated this current. What is the angle associated with current? It is determined by the power factor. So we have three cases. Number case 1 is 0.8 lagging power factor, and for this cos inverse of 0.8 will give us angle, and that is 36.9 degrees. And the angle for lagging power factor will be considered to be, the current will be like this. We will have a minus sign as we have done this previously also. So this will be the current for the lagging. For similarly for 0.8 leading, the current angle will be positive, and for 1 the angle will be 0. So which current are we talking about? So whenever we are talking about solving a circuit for voltage regulation, the magnetization branch is ignored. So actually the circuit is like this, and we have opted to use the circuit referred to the secondary side. So we know this is the current that we are talking about, full load current that we have taken 65.2 amps. This voltage is actually the voltage that is at the secondary side, or our load voltage, and this voltage is Vp over A, primary voltage, because here we can see this. So the books, there are two books, they follow different conventions for writing the notes. So this is actually Vh over A. So this concept should be clear in this scenario. So again, this is the current, and the voltage drop across this is VR. The voltage across this is Vx. So this becomes the equation. Now for the voltage regulation, we know the formula. This is V secondary no load minus V secondary full load divided by V secondary full load. So at no load condition, and when there is no load, the current is 0. This is actually the output of the transformer. So we can write this formula. It's full load, and sorry, this is secondary full load. Full load is the voltage that we desire out of the transformer. At full load, our transformer should be giving 230 volts, right? So we know this value and this value, but we have to calculate Vp over A by applying KVL here. We know Vp over A equals to VR, let's see, Vs full load plus VR plus Vx. We know the current, and so this will be 230 volts, angle 0 degree, plus current is for the lagging log, it is minus 36.9. So this will be I FL into R equivalent. This is R equivalent, X equivalent, referred to the secondary side. These are all referred to the secondary side, and we have calculated these values referred to the secondary side. And so this will become 230 volts. We know the value. What is the value? This is 65.2 minus 36.9 degrees, and this is our equivalent is 0.0445. Here we have shown, and actually this is actually 650065. You will calculate, you'll find the real values. And again here this is the same, this value is 0.0665645. Actually this should write it neatly so it is not a matter of confusion for anybody. But this is a solved example, you can find the values, and here also. So what we will get, we will the values that after putting the values, we will get the values as 2.9 volts. This will be minus 36.9, same angle as that of the current. And here there will be a 90-degree phase shift for the inductor. And that will be 53.1 degrees. And we can also calculate. So the value of Vp over A we can write as 234.85 angle 0.4. Similarly, this was for 0.8 lagging. If we want to calculate for 1, all the things will be same, only the angle will become, the current will become, full load current will become this for 1 power factor. And when we are considering 0.8 leading power factor, the current will become plus 36.9 degrees. That's it. And you can calculate the values. So the voltage regulation will now become this voltage regulation. Then we are coming back to the lagging load. This will be 234.85 and minus 230 divided by 230, and the value of this voltage regulation is 2.1%. And as we have also seen previously, we can draw the phasor equivalent of this. Let's see this. This is Vs. This is 230. Then we have 2.9 volts. The angle is minus 36.9. And then we have this value. This is 4.21 volts. And here is our 0.4 degrees. This is actually the resultant of the KVL. Okay, so this is how we are able to calculate this. And in the similar way, when we will calculate for leading load, we can create a phasor for a unity power factor. For the unity power factor, it will be something like this. This will be Vp over A. And for the leading power factor, as you have seen, the current is leading, so VR will be like this. This is the current. And then we will have the 90-degree, and this will be Vp over A. So this is how we can calculate the phasors. And in the last part, we are required to calculate the efficiency of the transformer at full load. So at full load, when the power factor is 0.8 lagging. So the last part is regarding the efficiency of the transformer. So let's do this. The efficiency of transformer is P out divided by P out plus P losses. We have copper losses and we have core losses into 100. So this is what we have to do now. So the P out for the transformer, for this transformer, we can see is the P out for the transformer will be Vs, Is, cos of theta. And they have told us that for 0.8 lagging power factor. So cos theta is 0.8. Voltage is 230 volts. And Is, that is the full load current, because they have required the efficiency at full load, and 0.8. So the P out will become 12,000 watts. Now to calculate the copper losses, we know the value of R equivalent S. We know this value. We know the value of the current. So we can calculate copper losses here. And this will be Is square into R equivalent. and this is actually 65.2 square into R equivalent. What is the value of R equivalent? It is the same, this 1045, and this will become equals to, copper losses will be equals to 189 watts. So here we have calculated copper losses also, we know output. Now we have to calculate the core losses. So to calculate the core losses are the losses that are actually occurring in this area. Okay, copper losses were occurring at this area in the series impedance, and the core losses will be occurring here. So what is the voltage across this? If you know the voltage across this, can we calculate the core losses? Yes. So yes, and this will actually become and RC is, what was the value of RC that we have calculated? It is 1050. Ohms, and this will become, copper losses will be, core losses will be, sorry, at 52.5 watts. Yes. So now can we find the efficiency? Yes, we can find the efficiency. This will be 12,000 divided by 12,000 plus 189 plus 52.5. So the efficiency of the transformer will become, if you calculate this, 98.03%. So that's how it is done. Students, I hope it helps. Thank you very much. Assalamu alaikum.